electrons. So not surprising that beryllium is in the second column. Now, boron has 3, 4, 5, 6, 7, and 8 back up to neon there, so it's not a shock then that boron has 3 valence in the third column. Carbon has 4 valence in the fourth column. Nitrogen has 5 valence in the fifth column. Oxygen has 6 in the sixth column. Fluorine has 7 in the seventh column. And now here we go up to neon, 8. And apparently at these early levels, the maximum you can get is 8, which is why we call this the octet rule. All right? The octet rule says it is 8 maximum in a shell. It's not quite true because apparently in the first valence you can fit 2. And we'll discover with subshells and everything later like that, you can go further than 8, but now we're getting complicated. So, anywho, taking a look at the first 18 where things are nice and neat and regular, this is your first shell that has 2. This is your second shell that has 8, and this is your third shell here that has 8 as well. All right? So what kind of problems are you going to get from this? Well, let's take a look at some of these. Oh, one other factor here. Sorry, forgot to mention this. Shielding. All right, so there's another concept that they're going to throw at you, and that is the concept of shielding. And the idea of shielding is just what it says here, which it says that inner electrons interfere with the ability of the nucleus to attract the outer electrons, and consequently, the outer electrons are easier to remove when there's more inner electrons that are there. What does that mean? Let's take a look at this nucleus. If this nucleus tries to attract that electron, well, there's nothing in between, so it can hold it in place. But if this nucleus here tries to attract an outer electron, well, before it can attract that outer electron, that inner electron is going to get in the way. And did you notice that those two electrons, because they're both negative, they're going to repel each other. And because they repel each other, that's going to make it harder for this nucleus to see those outer electrons. So shielding just says that inner electrons make it harder or interfere with the nucleus to attract the outer or the valence electrons. Thus, consequently, valence electrons are easier to remove when there are more inner electrons. So the more shells there are, the more shielding there is, and the more shielding there is, the energy drops. Think of it this way. If you went to go see a show, well, these people up here in the first row, they have nobody blocking their view. Well, they're not likely to leave at all because they can see the show no problem. But as you get further and further out to these guys out here, well, these guys can't see the show that's going on. They got all sorts of people that are in the way. And so these people that are out here, because they can't see, look at them all complain here. Oh, stop blocking me, move, I can't see. They're more likely to wander away and leave. And so they are easier to leave because there are all of these people that are shielding them from the show that is going on. All right? So as shielding increases, your energy decreases. It's easier to remove those. All right. So let's take a look at some examples now of the types of problems that you're going to see. It's pretty simple. Take a look at these examples here, sodium, potassium, and rubidium here. A couple of things to note from this data. First of all, you should see a big jump for sodium and potassium and rubidium after the first electron, and we do. A big jump here, a big jump here, and a big jump here. Why a big jump after the first one? We'll take a look. All of these guys, sodium, potassium, and rubidium, are in the first valence. And if they are in the first valence, that means they only have one valence electron. Everything else is on an inner level. So it's easy to remove that first valence electron here, here, and here. Past that, it's going to be more difficult because, again, let's look at these guys in turn. Sodium, if I remove number 11, now I got to try to remove number 10. Well, numbers 3 through 10 are in the next level down, closer to the nucleus, so that's going to make it harder to do. Potassium is the same way. If I try to take its outermost or valence electron, no problem. But then if I try to take the next electrons that are there, they're all on the next inner level in, and they're closer, and they're harder to take. Rubidium is the same way. If I try to take rubidium here, no problem. But if I take it, then I'm going to have to take more energy to take the next one because they are closer in to the next shell. Additionally, I want you to compare the numbers for sodium, potassium, and rubidium, but just compare them here, here, and here. And what do you notice? You notice that sodium is more than potassium, is more than rubidium. So they are decreasing. They are going down. They are easier to remove. And that makes sense. Here is sodium. Sodium's outer electron is only at level 3. Potassium's outer electron is at level 4. Rubidium's outer electron is at level 5. Rubidium has more distance and more shielding than potassium, which has more distance and more shielding than sodium. And both of those things make it easier for those electrons to be removed. So as you go down a column on the periodic table, it becomes easier and easier to remove those electrons. Here are two more examples. Magnesium, calcium, and strontium. This is identical to what we just saw. Magnesium, calcium, and strontium. Here they are. Boom, boom, and boom. The only difference is that because they are in the second valence, you should see a major jump after the second set of ionization energies, which is here. So we see a sizable jump between 1 and 2, but a huge jump between 2 and 3 here. An enormous jump. Same thing here. A sizable between 1 and 2, but then an enormous between 2 and 3. Same way for here. A sizable one between 1 and 2, but then an enormous one between 2 and 3 there. So, consequently, each of these guys is in the second valence. But then if you compare magnesium to calcium to strontium, strontium is further away because it's lower on the periodic table. It's at the 5th energy level as compared to 4 and 3 for calcium and magnesium. And so consequently, strontium's numbers should all be less than calcium and magnesium numbers. And if you compare, strontium is less than calcium is less than magnesium. Strontium is less than calcium is less than magnesium. Strontium is less than calcium is less than magnesium. All the way across the board when you compare similar ionization energies. One last one. What if I gave you this and said one of these is aluminum, one of these is calcium, and one of these is strontium? Could you figure out which is which? Well, the answers are there, right? Pretend they're not. Let's pretend those answers aren't there for a second. Say you didn't know that this was this and this was this. Could you figure out which one is which? Well, if we take a look at these on the periodic table, you should be able to tell that aluminum is in a 3 valence, and calcium and strontium are each at 2 valences. So let's see if we can't find that. So it looks to me like there is a huge jump here between 2 and 3, so that would be a 2. It looks to me like there's a huge jump here between 3 and 4, so that would be a 3. And it looks to me like there's a huge jump here, so that would be a 2. So consequently, this one has to be the aluminum, and of course it is, because it's the only one of those that's a 3. Now both calcium and strontium are in valence 2 here, right? But strontium is further away, and if strontium is further away, then that means it should be less. So we take a look, this one is less than this one is less than this one. So yeah, that one's got to be the strontium, and that one has to be the calcium.